This lesson deals with the vector representation of sinusoids. You can find these notes in the course ebook in Chapter 4, starting on page 7. Suppose I take a function f of t that's equal to f of a times the cosine of omega t plus phi. Let me represent that as a vector. Have the length of this vector equal to f of a and an angle of phi. Now suppose I create another set of axes, this y-axis and this x-axis, where this is the function f of t versus time. At t equals 0, what I've got is f of a times the cosine of phi, and that has this particular value. If I were to project that onto this y-axis, that would be the value of my function f of t at t equals 0. Suppose that this vector is rotating at an angular frequency of omega. As time is increasing, eventually get to the point B. And that's going to be at some time later, and I project that onto my axis. It would be over here. Continuing on, I would eventually create the cosine function, starting out at t equals 0. This rotating vector was proposed by Charles Steinmetz in 1893. He's sometimes called the father of electrical engineering. He basically figured out a way to explain AC circuits. It was later coined as the phase vector, or just simply the phasor. Now at t equals 0, this vector is stationary, and we call that the phasor. It has a length of f of a and has an angle of phi. If we do a problem with other voltages and currents, they'll have the same frequency as our original problem, because if we integrate or differentiate a cosine, we get a sine back, but a sine is really a cosine just phase shifted. We represent different voltages and currents by different phasors that have a length and an angle at t equals 0. Since they all have the same frequency, these vectors are rotating at the same angular velocity. A sort of merry-go-round exists on which all of the vectors are riding. This merry-go-round is called the frequency domain. If one is in the frequency domain revolving with the vectors, they appear to stand still. Thus the amplitude and angle of voltages and currents can be captured by stationary vectors or phasors at t equals 0. Since all of the phasors in any given problem are on the same merry-go-round, they are stationary with respect to each other. We'll show later in this chapter that phasors can be manipulated by ordinary algebra rules of vector geometry or vector algebra. When the resultant vector or phasor has been obtained, its projection gives the time function solution to our analysis problem. Stepping onto the merry-go-round is called transforming the problem into the frequency domain. The resultant vector in the problem is called the frequency domain solution, and the process of finding its projection is called transforming the resultant into the time domain. This is like stepping off the merry-go-round. Let's next take a look at a complex algebra representation of phasors. And this is on page 9. Let me start with what's called Eulers Formula, or Euler's identity. And that is e to the j theta is equal to the cosine of theta plus j times the sine of theta, where j is the square root of minus 1. In math, we used the letter I for this, but we're using I for current. So we're just going to take the next letter of the alphabet. We can represent vectors two ways. One with a magnitude and an angle, but also a projection onto the x and y axis. That projection we call the rectangular form. Just given any number n has a real part plus j times an imaginary part. We could also represent that as a length at an angle. C times e to the j theta. Sometimes we just use a shorthand notation for this of just the angle of theta. Let's take a look at how we might interpret this. If we have a number that's complex, we represent it as a magnitude and angle, c times e to the j theta. Again, by Euler's identity, this is equal to the cosine of theta plus j times the sine of theta multiplied by c. This would be our real part, and this would be our imaginary part. Call it just re and im just for short. If we had a vector that had a length, say c, and an angle theta, we could project it onto the x-axis and onto the y-axis. You may recall from algebra that the projection onto the x-axis is the length times the cosine of the angle. The projection onto the y-axis is the length times the sine of the angle. If you started with this, you could find the length, because this is a right triangle, by taking the square root of the square of the sides. A squared plus b squared, square root is equal to c. That would be the length of our phasor. The angle is the arctangent of the imaginary part over the real part. Given this representation where we could measure this or this, we could then find the vector length and the angle theta. Just some notation. The cosine of theta is just a real part of e to the j theta, and the sine of theta is the imaginary part of e to the j theta. Given v of t as having some amplitude and some angle, and some frequency, as v sub a cosine of omega t plus phi, we could write the cosine as the real part of e to the j of this argument of omega t plus phi. We can also write this as e to the j omega t times e to the j phi. When you multiply these two, their arguments would add, and we get back to this. I'm going to bring this scalar v sub a inside, because just that is a scalar, and I'll put it with the second term. Pull that over here, put this term over here. What is this? This is our phasor. It has a magnitude and angle, and this is our rotating angular frequency. V of t in a time domain is the real part of these two quantities. We're going to suppress this while we solve the problem and just work with the vectors, and then we'll put this back in at the end, because they're all rotating at the same frequency. Now, in many textbooks, they use the bold letter to represent the phasor. That's a little hard with handwriting, so I'm going to use the letter with a broken arrow on top, so we won't confuse this with current. That's simply going to mean that I have a length of v sub a and an angle of phi. This is going to be called our phasor transform from the time domain to the frequency domain. So in the frequency domain, we're going to solve our circuit problem and come up with a resultant voltage or current. Suppose that that's equal to V. The inverse phasor transform is putting this back into the time domain. We have to multiply this by e to the j omega t, taking the real part of our phasor, and then we'd suppress this rotating frequency, and then put this back in as v sub a times e to the j phi, bring the v sub a out. I've got the real part of e to the j phi times e to the j omega t, and I put those two together as j quantity omega t plus phi. And then using Euler's identity, this is going to be the cosine of omega t plus phi plus j times the sine of omega t plus phi. But we're taking the real part of it. So we're just taking this part here. So we're back in the time domain with a new amplitude and a new angle from where we started. The inverse phasor transform transforms the frequency domain result to a sinusoid in the time domain. This sounds pretty complicated, but we'll see in a little bit that that's a fairly simple process. And this is the vector representation of sinusoids.